Hi, welcome to Mechanical PE Exam Prep Question of the Week, the series where I solve mechanical engineering problems for aspiring professional engineers. In this video, I'll answer the question, where should you take the specific volume from on the psychrometric chart? This is a question that's been asked over and over, so there's obviously some confusion out there. Today, we will clear it up once and for all. So let's take a look at the psychrometric chart. Let's go through two different examples. The first example I want to look at is a case where we have only sensible cooling. So let's imagine it's a typical temperature in a room. Maybe it's 74 degrees and 50% humidity. And you're doing some cooling with a chilled water coil, but the chilled water temperature is warm enough that the cooling that's happening is only sensible. So maybe your chilled water temperature is pretty high, we'll say 60 degrees. Then your process line might look something like that, where this is state 1 and this is state 2. And the question comes up, where should you take the specific volume if you want to use the classic rule of thumb, Q dot equals 1.08 CFM delta T? Well, the first thing I want to say about this is it's not too important, right? Like this question comes up a lot, and I think people spend a lot of time thinking about it because they've been burned at some point doing a practice problem where it mattered. And once that happens one time, it makes people paranoid that they have to constantly obsess over making sure they select the correct specific volume. It is worth thinking about, but I just want to point out that the specific volume doesn't change that much, right? I just picked this for a typical example, but if we go with this is maybe 13.65 here and 13.3 here. So not a tremendous difference. Will that throw off your answer a little bit? Yeah, it will. But if the answer choices aren't that close, or you're just looking for a quick back of the napkin calculation, put yourself in a real engineering situation, right? Forget about the PE exam for a minute. If you're off by 2 or 3 or 4% when you're sizing a coil or something like that, it's not the end of the world. And the spirit of the PE exam is not to force you to have the sharpest possible pencil when you're solving these problems. It's to see if you understand air conditioning processes and you can make a reasonable set of assumptions to get the solution. So my concern is that you become a better engineer. I want you to get the big picture and see what's going on. That said, we'll get into the detail here. So what's actually conserved as air flows over a coil? Let's draw a coil. So we have this entering air coming at state 1. That's our room condition. That was our 74 degrees, 50% relative humidity. And that's state 1. And that's coming over the coil, and it's coming out at some other temperature, maybe 60 degrees, and it looks like the humidity is about 80%. Fine. And that's state 2. Now, since this is purely sensible cooling, there's no latent cooling, which means no water vapor is coming out of the air. The air is just getting cooler. So what's actually conserved in this process of flowing over the coil is the mass of air. So we can say m.1 equals m.2. The amount of air that entered the coil is the same as the amount of air that leaves the coil on a mass basis. It would not be correct to say that the volume that enters the coil is the same as the volume that leaves the coil, because the volume changes. Why does the volume change? Because the density changes. As warm air gets cooled, it becomes more dense. So that means there's more mass per unit volume, so you need less volume to hold the same amount of air. Let's say that with a bit more detail to back it up. What we're saying is that V dot, the volume flow rate entering the coil, is greater than the volume flow rate that leaves the coil. Again, slightly. This is not something to obsess over. This is a slight difference. And why is that the case? Well, density is mass over volume, right? So we can replace, let's write that down. Density is mass over volume. So if we're going to write M1 equals M2, we can replace both of those with rho 1 times volume flow rate 1 equals rho 2 times volume flow rate 2. And since the density is the reciprocal of the specific volume, we can write that as V dot 1 over little v 1 equals V dot 2 over little v 2. So if you're wondering how much less is the volume leaving the coil, the volume at state 2, compared to the volume at state 1, we can rearrange this to write the ratio of V dot 2 over V dot 1. Let's do that algebra now. V dot 2 over V dot 1 equals little v2 over little v1. So really no surprise there. The ratio of the volume flow rates is directly proportional to the ratio of the specific volumes. So in this case, that might be something like 13.3 over 13.6.5. That's about 0.974, so call it 2.5%. That's how much it'll change your answer by in a typical case. And why does that actually matter in here? Because you're choosing the CFM. So you're plugging into the rule of thumb what the volume flow rate is. Should that be the volume flow rate at state 1 entering the coil or state 2 leaving the coil? The answer is it doesn't really matter as long as it's the right volume flow rate. So if the problem statement tells you the volume flow rate entering a coil is 10,000 CFM, then you should use it for V1. If they tell you the volume flow rate leaving the coil is 10,000 CFM, then that tells you the volume flow rate entering the coil is probably slightly more, maybe 2.5% more. If you can accept an answer that's off by 2 or 3%, then you can use either one. But my short answer to this question is you should use the specific volume for wherever the volume flow rate is given. So if you're told the volume flow rate entering the coil, then you should pick the specific volume at state 1 for the air that's entering the coil. So in this case, you would pick 13.65. So really that's more than we should ever need to say about this topic for purely sensible cooling. But let's take a look at a slightly more interesting example, which is a proper air conditioning process where you're doing not only sensible but also latent cooling. All right, now let's take a case where it's a bit warmer in the room. We'll say it's 75 degrees and 65% humidity, and that'll be our state 1. And we're cooling to 55 degrees saturated, and that will be our state 2. So now we have both sensible and latent cooling happening. So now, what does that change for our coil situation? Let's draw the coil again. We have our 75 degrees and 65% humidity and M.1 entering the coil. But now we're going to do some latent cooling, which means that condensate is going to be removed from the air. Water vapor is going to be removed. So let's draw a little drip pan underneath the coil here. We have M.condensate leaving the airstream, and then M.2, which ultimately leaves the coil, is at 55 degrees and 100% humidity. Ultimately, we'll probably do some bypass and some mixing, but I don't want to complicate things. The point of this problem is to illustrate that the mass flow rate entering the coil is not equal to the mass flow rate leaving the coil. They're not conserved because the difference is the condensate that drips out of the airstream. So the equation that we would write instead would be M.1 equals M.condensate plus M.2, with the big point here being that M.1 does not equal M.2. So here, M.1 did equal M.2, and the difference between the volume flow rates entering and leaving the coil differed only because the density changed. Here, that's still true. The density is changing as we go from 1 to 2, but we're also losing mass because we're removing water vapor by means of condensation. So for an air conditioning process that involves latent cooling, which most air conditioning processes do, you really want to use the volume flow rate at state 1. You want to use the air entering the coil because that volume flow rate, V1, corresponds to M.1, which contains all of the mass of the air and the mass of the water before it comes out. The only exception to that is if you're analyzing something that happens after the coil. Let's say your problem statement tells you the volume flow rate of supply air leaving an air handler. Maybe it's 10,000 CFM, leaving the air handler and going into the room, and then you're dealing with the heat load in the room and trying to figure out what the delta T is, or something like that. Then you're going to take that volume flow rate leaving the air handler that's going somewhere else and follow it there and see what happens next. But if you're really analyzing the air conditioning process, you're analyzing the coil, and you're given the volume flow rate at state 2 leaving the coil, you have to realize that the mass that corresponds to that volume flow rate is not the entire mass that entered the coil because of that condensation that makes up the difference. So you'd have to work backwards. And how would you do that if you had to do that? There's not very many problems, by the way, that will ask for you to do this, but you should understand it, at least on a fundamental level, that this is what's going on. You could figure out how much mass was lost. Usually this question would be a lot more straightforward because they would say how much condensate is removed by an air conditioning process that does something like this, right? You know the humidity ratio at state 1 and you know the humidity ratio at state 2. So you could find the mass flow rate of water or condensate is equal to the mass flow rate of air times the difference between those two humidity ratios, 1 and 2. Where the mass flow rate of air is the mass flow rate of air at state 1 because that contains both the air and the water. And it's the difference in mass of water per mass of dry air. So you really want this mass flow rate of air to come from the volume flow rate at state 1 and the specific volume at state 1. So if you find yourself in a situation where you want to use this rule of thumb and you only know the volume flow rate at state 2 leaving the coil, you would have to recognize that this CFM plugged in here will lead you to understate the heat transfer that's actually happening because you'd be missing out on the mass flow rate of water vapor that was part of the entering airstream. So I'm probably belaboring the point here. Hopefully this has been useful and hasn't led to more questions. I hope this has answered some questions. And if nothing else, just drills down to a level of detail where you're thinking about the specific situation and what kind of a process is going on and figuring out what you need and why you need it, rather than looking for some simplistic answer of always take it for the air entering the coil or always take it for the air leaving the coil. I think if you were really looking for a short answer, you'd say, well, we prefer to have it for the air entering the coil. But again, like the example I gave, if you take it for the air leaving the coil, you might be interested in what's going to happen after the air handler, something that's going on in the room or a reheat process or something like that. So really, the ultimate answer is it depends. But with the caveat of don't worry about it too much, most of the time, it's not the end of the world if you pick one or the other. The one thing I would watch out for is the extreme cases where you have very cold outside air entering a system, cases where you have a tremendous amount of latent cooling happening. Imagine this sensible heat ratio was such that the line ends up being very steep. You're removing a lot of condensate. You're going to have a dramatically different mass flow rate at 1 compared to the mass flow rate at 2. So you want to watch out for those extremes. But in a very typical air conditioning process where you have comfortable room air at a normal temperature and humidity, and it's being cooled to 55 degrees, you can use this rule of thumb all day long, and you will very rarely get burned. So that's all the advice I can give around this point. If you still have a question around this topic, I would say don't ask it generally, ask it specifically. Send me a specific problem where you're not clear on whether you should take the entering air or leaving air or something else, and let's deal with it on a case-by-case basis. I can't give any more general guidance than what I've offered up here. All right, guys, hope you found this useful. If you're a mechanical engineer studying for the PE exam and you'd like to get your question on the list, the best way to do that is to send me an email at dan@mechanicalpeexamprep.com. And if you want to make your study process as efficient as possible, sign up for my courses if you haven't already. First, you get the fundamentals, and then we do lots of practice problems. It's a great way to give direction and clarity to your preparation and take your studying to the next level. It's what I wish I had when I was in your shoes. The best way to get the courses is directly through my website. The price is lower than it is on Udemy, and if you use the link below and the coupon code MEC10, you get an additional 10% off. Until next week, happy studying.